De førerløse biler. Vi skal høre lidt om teknologien bag, og også lidt omkring de data, der ligger bagved. Vi har fået meget fint besøg i dag i form af professor Alberto Broggi fra Parma Universitet, som har udviklet en førerløs bil. So, welcome to you, Alberto. We are looking forward to your presentation.
Thank you very much, Jesper. And good morning, everyone. My name is Alberto Broggi, coming from the University of Parma in Vislab. And I would like to start with a big thank to Jesper, of course, and the whole organizing committee for inviting me and us being here today, giving this presentation, and also showcasing our car that we have parked outside. And I will be coming back to that in a couple of minutes. Well, today I will be touching one specific topic, which is autonomous driving. I will be giving you some perspective on autonomous driving. But first I would like to just mention who we are and why we're doing this. So we are a team of about 20 people based in Parma, Italy. We started as a university laboratory back in maybe 15 years ago, a little more than that. And then we developed our technology for autonomous driving when autonomous driving was not so fashion. Now everybody's talking about autonomous driving. But when we started, actually we were just a few crazy people working on cars that should be driving by themselves. Then in 2009, we started our spin-off company within the university, and now we are in our fourth year of this spin-off company, which is working together with the university. And what I would like to do today is to show you what we have been doing. I have just a couple of slides on what we have been doing in the past, in the last more than 15 years, and then show you what we are doing now and which is our perspective and our ideas on autonomous driving. So I will just show you a couple of video clips, kind of old. That's 1998 when we first drove with our passenger car on Italian roads, and that's 15 years old. And we had 2 video cameras behind the windshield, and 1 PC, which was a Pentium 200 megahertz. That was a kind of very conservative technology, if you look from today, from a perspective of today. And that was the very first test on real roads with an autonomous car. And then at that time, that wasn't fully autonomous. That was 94% autonomous. So the rest, the remaining 6% was driven by hand by someone behind the steering wheel. And then we actually participated in the DARPA challenges. Maybe you are familiar with that. Those are challenges, so races between autonomous vehicles, no driver at all. And we were the guys behind the perception layer of that big yellow truck that was able to reach the final finish line of this race. And you can see we had the first race in 2005. The vehicle was able to negotiate off-road terrain. 2007, the race was downtown, in a simulated downtown area. And then the vehicle was able to handle all the situations common to urban driving. Then actually we took our technology and we are putting our technology also on other vehicles. So not only cars and trucks, but also dozers, implements for agricultural, tractors, mining vehicles. So we're trying to move our driverless technology from the automotive domain to many different other domains. And those are examples of vehicles that we have been working with, and we have been putting our sensing on it. Okay, so the main challenges for autonomous driving are, so you should split the autonomous driving thing in 3 different layers. So the first one would be understanding the environment. The second one would be taking decisions based on what you have seen around you. And then the third part would be actuation. So once you have taken the decision about accelerating, decelerating, steering, or whatever, you should be able to have the vehicle interact and react to your to the trajectory. So these are the three big steps for autonomous driving. And we're mainly focusing on the first one, which is environmental sensing. But I would add something more here. So not only the technical aspects, but once, in a few years, someone will produce autonomous vehicles. And we had some very nice, very strong claims lately by some car makers saying that they will be able to sell autonomous cars by 2020. So in just a few years from now. And if you're considering that someday someone will produce autonomous cars, you will have to consider also other issues, like, for example, the cost, the integration of the sensors on the car, robustness, redundancy. This is a huge problem because this is a safety critical issue. So if something fails, the car should be able to react and, for example, come to a complete stop before hitting somebody else. Security. This is a huge issue. For example, this is hiding the problem of hacking, of someone getting into your car from a remote location and changing the behavior of the car or changing the parameters of the car. So those are really, really important issues that get more importance as long as you get closer to the market. So currently, all the research centers are mainly working on the first three steps. Just forget about the product. Someone else will be talking about that. Someone else will be considering that. But what we are doing is that we're focusing, and this talk is mainly about this, focusing on sensing with a special perspective based on reducing cost and increasing the level of integration. And that means that we're not only searching for the best sensor, but we're searching for the best sensor which has a reasonable cost and can deliver a nice integration in the car. So we are adding some more constraints to the problem. If you have seen some videos or pictures or even YouTube videos that shows the Google car and many others. I mean, the Google car is the most, I think, the most famous one, but there are many others. It's not only the Google cars. There are many other research centers worldwide that are working on autonomous cars. You may have seen that they are using this 3D laser scanner, which is put on top of the roof of the car, and that delivers a wonderful set of 3D points all around. It gives you, I guess, 2 million 3D points per second, and it rotates in 10 hertz, so you get up to 100 and 120 meters far away in all directions. So it's 360 day and night. It's a very generous technology that can deliver a lot of information for the car to drive by itself. You may have also seen some pictures, and the first one actually is a Google car that use this sensor, and I just put it around a circle around the sensor on top of the roof. So those are, I didn't want to be exhaustive, but those are just 4 vehicles that are using this sensor. It's a great sensor, and it's really reliable. It's wonderful. But if you come to a closer look at that possibility of integration on a real car, that becomes quite complex because the sensor is very high on top of the roof. It spins at 10 hertz. It's quite expensive now, but the cost will be decreasing as the technology will improve. But they also need some kind of expensive inertial platform. So if you look from a distance, this is a great technology, but has some drawbacks. And what we're trying to do is overcome these drawbacks with a different technology. Maybe it's not as mature as the technology that you can see here, but it's kind of promising. And I would like to now to show you what I mean with that. So this is a picture of the Google car. This is very famous. And if you look closer to that, the one on the top is this 3D sensor. It's a 3D laser which rotates and delivers this great amount of data. But unfortunately is sitting on top of the vehicle. So that's the Google car, and I took the Google car because that's one of the most famous vehicles, but there are many others which are using that technology. And this is our car. This is the car which is parked outside here, and you will be able to have a look at that after the presentation, after the morning session. So as you can see, our car is mainly based on small sensors hidden around the car. We don't have any big sensor on top of it. So this is a key word for us. So we're trying to reach a high level of integration with sensors that are cheap. So we are mainly using cameras and not big laser, 3D lasers. So our approach is based on, the two keywords are low cost and very deep integration. So this is something that we have been always being used as our main keyword for our research. So not only try to solve the problem, but solve the problem with a constraint problem. So with these in our mind. So low cost and highly integrated. And just to show you what I mean with that, well, you can see in this video, this is a video taken from a camera installed on a vehicle, one of our vehicles. And well, this is, you have seen that many times. But if you put together two cameras, so with stereo vision, two cameras at the same time, and you also put a very smart algorithm for stereo reconstruction, so this is what you can get. And this is a color-coded image. Red means far, green is close, and you have all the shades in between. And as you can see, you can get pretty nicely for almost every single pixel a distance estimation. If you put together the two things, so the color image there and the distance image here, if you put them together, you have a 3D point cloud, and you can plot the 3D point cloud in this way. So this is a 3D image, and you can then move your camera, virtual camera, in this 3D point cloud. And remember that this is just two images with a smart algorithm, just two images put together. You have triangulation for every single pixel, and then you get this very dense 3D point cloud. You will see how we use this, for example, to determine the slope of the terrain. If the terrain is flat or the terrain goes uphill, downhill, you will see from this perspective that we were able to get even the roughness of the terrain in front of us. And look at the object. The object is quite, the shape of the object is very smooth. So this is just to give you an idea about the kind of data that we are using on the car. Well, the front part, of course, is missing because we are looking from the back. Okay, well, that was just an example. This is another example of a 3D point cloud. And you will see now two different objects, two obstacles, two pedestrians, and you can look at them from different perspectives. Again, I just wanted to show you this video clip because this is what you get 10 times per second on our car, and that's in real time. So every 100 milliseconds, you get one shot like that with all the 3D points. Then you take all the 3D points together and you glue them together, you cluster them together, you process them, and then you have the representation of the frontal part of the vehicle. So this is again done just by vision. So we're not using any laser or any very expensive sensors. And I will be coming back to this technology at the very end of my presentation to show you our current trend and our current technology on this. Okay, so the next step, I just mentioned that we have many 3D points, a very dense cloud, 3D point cloud. And then the tricky part is to label every single pixel, every single 3D point as belonging to the road or belonging to an obstacle. So this is kind of tricky. I will not go into the detail about that, but this is what you get at the very end. So all the points that belong to the road will be used to approximate the terrain slope. And all the points that do not belong to the road will be left untouched there. So you will see that we are able to locate the ditches, the hills, and well, there's also a bump here. You will see it here. There's a ditch. And we will leave all the obstacle points behind. So the obstacle points, like, for example, the tree here, is still there. So that's the intermediate processing. Once we have done that, we have the information about the road slope, terrain slope, roughness. Then you're going to focus on the objects. And if you're now taking into consideration not the points belonging to the terrain, but the points belonging to the objects, you will try to label every single object based on its distance from the vision system. And this is what you get at the very end. So you will see on the left-hand side that we have the 3D terrain mapping. Then for every single object, we paint every single object in different color based on the distance. So, for example, the cars and the hill are painted differently based on the distance. And on the right-hand side, you have the top view. So our car is here and is looking forward in that direction. So you will see that every single slope is painted in red and the flat areas are green. So if you want to determine your trajectory, you will be looking at just the green part and try to stay within all the obstacles. So that's what we're doing in real time on the car. And the final step would be this one. So every single object will be connected and glued and clustered in this way, so that you will be giving an ID to every single object, and then you will be tracking every single object on the road. And this is an example of well, flat terrain, because we're driving on a road, and then you will be able to locate every single object, track every single object, and get the speed information of every single object. And this, again, is done in real time. So I just wanted to show you this because we're doing this without any laser information. Then, of course, we are fusing laser data because we're using vision plus lasers, simple lasers, because we want to use two different technologies, not only one, because if one fails, then you're done. So if you have two technologies, they will be complementing each other. And so we have been, as I mentioned, using stereo vision, two cameras, look in the same direction, and then triangulating the information. So the most important thing when you use stereo vision, if someone has been using that, will know that calibration is critical, is really critical, because you need to understand and know and keep the calibration of the system for a long time. So keep the positioning and the orientation of the cameras. So first discover the orientation, then keep them. Unfortunately, when you are on a car, it happens that temperature cycles and vibrations, and I mean, there are a number of problems on the car. So when you move around, maybe the one camera moves, the other doesn't, or one camera gets tilted and the other doesn't. So you are losing the original calibration. So what we have developed is a system that tries to change and adapt the calibration on the fly. And you will see now a video clip on our car. This is the car that we have outside. These are the different monitors, and the displays show what I've been showing before. So red is far, green is close. So this is a color coding of distance. And you will see that it's working nicely, but the guy will touch one of the cameras, so change the calibration, the system stops working. But after a while, the system, after a recalibration, picks back the calibration. So the nice thing is that if you change the position of the camera, you get blind for a couple of seconds, but then it picks up the calibration again. And this is really a must-have if you really want to do serious obstacle detection, terrain mapping, using stereo vision on board. So this is something which is working on our car and has been working for some years now. And now I would like to show you some real road experiments that we did to improve the perception and to try to push our technology to the limit and see what we can gain and what we can reach with our low-cost technology. So we have been testing Brave. Brave is the name of the car that we have here. Brave stands for Brain Drive. We have been testing Brave for a number of years now. We originally developed the car in 2009. So we have been using that for 4 years now. So we have been testing that in parking spaces, in different, that was downtown Rome, some specific locations. But in 2009, 2010, we've been testing that, and what we concluded at the end is that perception needed to be made more robust. So we needed really to work on perception, because perception is really complex. You are facing a number of different issues while we drive. So in 2009, we thought about doing some nice long test. So we put the same technology that we have on Brave on these kind of small vehicles. This is an electric vehicle that we equipped with more or less the same sensors, the same vision, the same lasers, the same processing that we had on Brave. And actually we developed 4 of them. 4 vehicles like them. So these are just replicas of one another. So exactly the same vehicle, exactly the same processing. So these are just replicas. And then we put together 4 of them. We put together 4 motorhomes, 3 trucks, and then we started our big test. So we started from Parma, Italy, and we ended up in Shanghai, China. We've been traveling for 3 months with these vehicles, autonomous vehicles, electric vehicles, and we just wanted to test the capabilities of the system. So mainly we wanted to address the problems and understand when the system was not able to handle the situation. And we recorded everything. So we recorded 3 months of driving. We had a really huge database of all the situations that we met. And in the end, when we came back into the laboratory, we processed some chunks of this data just to improve the system, just to learn a little bit. And now the version that we have of our software is much, much more advanced than what we had back in 2010 when we traveled from Parma to Shanghai. Yeah, you will. We did that with a trick. We had a trick because unfortunately, we didn't have maps for most of the trip. So we didn't have maps of Kazakhstan. We didn't have maps of China, Russia. So most of the areas that we covered were not mapped, even on Google Maps. So before leaving, we checked on Google Maps, which was the best route to reach Shanghai, but there was no routing because there were no real maps available. So the way in which we solved the problem is the following. Actually, it was a trick again. So if we had only one vehicle, that vehicle wouldn't be able to do any autonomous movement because you don't have a map. So the vehicle doesn't know whether to turn right, left, stay on the road because you don't have routing. So autonomous routing was impossible. So the trick was to add a new vehicle in front. So the vehicle in front was, manned. So people were in the vehicle taking decision about the route. The second vehicle was following autonomously. So the second vehicle was able to locate the vehicle in front, track it, and then follow it. Plus, we had also sensors on it, and the sensors were able to locate lane markings, obstacles, and pedestrians, and so that to stay in a safe position. But unfortunately, you understand that taking this, following this configuration for 3 months in 13 or 14,000 kilometers in different regions, that's impossible. And there was a situation in which, for example, the first vehicle was not visible because it was too far away, or there were vehicles in between, or was behind a curve. So we were not able to locate the vehicle in front. So the trick was that the first vehicle was sending GPS information from that vehicle to the second vehicle on a radio link. So it was kind of creating a map on the fly with the information that the first vehicle was detecting. So the first vehicle was driving, sending the GPS back to the second vehicle, and the second vehicle was autonomous. So that was a trick. But again, the whole thing was designed to have a nice test of our technology. So to understand whether our vision system was able to handle all the situation or not. And there has been many situations which required us to take control of the car and get back to manual driving. So these are just a few video clips that shows the different situations. So nice testing here on the bottom right, bad weather and off-road. So many different situations. And again, we recorded everything. And that was very important because with all the data that we gathered, we improved the system. And you can see different behaviors here. This is again the same sketch that I showed before. So you have the original video up there, and then the terrain mapping and obstacle detection and tracking. So you will see that when in a traffic road, we get all the vehicles and we track them all. In off-road environments, you're able to locate the berms on the right-hand side, on the left-hand side, even negative obstacles, so holes in the ground. And nevertheless, you're still able to locate obstacles like cars and trucks. We have been hitting some nice dusty roads and bad weather conditions. So we've been testing over a number of different situations, continuously improving the algorithms. And what we reached at the end is a kind of robust system that is able to locate objects, define the terrain slope in front of us. And then we wanted to really test the whole system. And this is what we organized last July. So a couple of months, 3-4 months ago, we decided to take a new demonstration, and we did that in Parma, downtown Parma. This is a tour that we designed. So we started from our university campus, which is in the south. We drove up to the north of Parma, through a ring, so it's kind of a highway-like scenario. And then we drove downtown until the pedestrian area downtown. So we had to manage all the urban environments, like pedestrian crossings, like roundabouts, traffic signs, traffic lights, and whatever. So this is a test that we took, and again, it was divided into 3 parts. Rural part, just outside Parma, then 2 freeways, and then the urban environment. And the reason why I'm showing you this is that most of the autonomous driving systems and tests have been taken on freeways and rural roads. So kind of I don't want to say friendly environment, but it's not that complex. The most complex part is the urban part, because the urban part has many it's very dynamic. So you have pedestrians, you have other vehicles. The behavior is not really that simple. Even the structure of the environment is complex. So we had a few kilometers driven in the urban environment, and just wanted to show you what I mean with the 3 different parts. So with rural, we're meaning narrow roads, 2-way roads in the countryside. Freeways, well, you know about that. The most difficult part was tunnels, but that's not really a big, difficult problems. But urban driving, I'm meaning this, so big roundabouts, underpasses, pedestrian crossings, complex behavior of the other road participants. So just to give you an idea, this is the part that we drove to reach downtown from the Parma Ring up to the north down to the pedestrian area. And these are the hot points. So the points where there might be some issues, like pedestrians, there might be roundabouts, traffic lights, tunnels, and we had to handle them all. So understand how to handle every single roundabout and handle it in traffic, in normal traffic. So I have some information about the sensing that we have been using. So this is again mainly vision based. So we have a camera on the car, and this is the car which is outside, so you will see that afterwards. We have a camera which is looking for the traffic signs, traffic lights. We have two cameras, stereo cameras, looking for lane markings, looking for obstacles in general. A sideways cameras. This is a cameras which is very hidden. You will not be able to see that. It's a camera which is looking on the sides to detect oncoming traffic in roundabouts or on verging. And then a camera looking backward to locate vehicles which are oncoming from the left-hand side. Then we have all the symmetrical parts on the other side. Plus cameras looking backward, which we didn't really use in that test. These are just for, these cameras are just for backing up. Plus we also have lasers, of course. As I mentioned before, we have two different technologies, vision and lasers. So these are three lasers which are installed in two front corners of the car and one in the back. Plus we have additional lasers with a increasing performance level just in the frontal part. And this is the vehicle that is outside, so you will be able to see all these sensors. And this is the internal part of the car. We decided to divide the internal part in two parts. So we have two passengers in the back seats. We have one technician on the right front seat. This is just a person that is there just to check that the system is working correctly. And then we have we call it safety inspector. So it's a guy that is sitting there ready to take over just in case. So if something happens, this guy is ready to grab the steering wheel and press the pedal and stop the car. And the final part of this test was driven without anybody sitting in the left front seat. So that was finally vacant because we removed that guy there. So this is something we're trying to do even today, so you will see that. We have put the whole recording of that day on YouTube, and this is a kind of long video, but you will see that it's an uncut video, so you will see everything that happened on the car that day. So there's no mounting of different images, no cutting, so nothing hidden, as you may have seen from other tests that just show you just little pieces of what's happening. So in this case, you have the whole video, and you will be able to see the vehicle itself, an image taken from the vehicle, and all the vehicle data like speed and steering angle, the status, the internal status of the vehicle, like looking for pedestrians, looking for a traffic sign, looking for whatever roundabout or. So that's the internal status of the car. And these are just examples of the vehicle taking a roundabout, kind of complex roundabout, under a pass, under a ring. And that's quite complex because you don't have precise GPS in that situation. We'll come back to that later. This is another example of merging. During our test, we had to change the highway. And that's our vehicle. This is our vehicle. It's not the first one. This is our vehicle that was stopping and waiting for the other cars to pass. And then when the road was clear, the vehicle started driving on the highway. So that's another example. And I would like to show you some other nice examples, like going into a canyon and then down in a tunnel. So in this case, GPS will not work. And as you can see from the image here, when you get out of the tunnel, you're kind of blind for a few milliseconds because the camera will need to adapt to the outdoor and illumination. So, well, cameras will not work for a while. So GPS is not working because you have the tunnel. Cameras are not working because you get blind. So the other technology, the laser technology, will help you and will be able to locate the objects and obstacles and keep you inside the lane. In this case, there's a traffic light, and you will see the vehicle that when the traffic light gets green, it will start again. And that was the very last part when our safety driver got off the vehicle, and we drove for the very last part of the test without anybody behind the steering wheel. And that's, again, the very last part was a stretch of road involved and the roundabout, and then we stopped at the very end. Okay, so I would just summarize the results of that test. It was about 13 kilometers, 3 of them driven in an urban area, driven about 18 minutes, and we didn't do that at 2 a.m. on Sunday morning. We did that at 11 a.m. on a working day. So we wanted to do the test on a normal traffic pattern, not on a specific traffic pattern, or we didn't have the police in front of us to keep everything to keep the road clear. We didn't have that. So we actually was moving in real traffic and real scenario. And we didn't have any human intervention. So we started the vehicle at the university campus and we stopped the vehicle downtown in Parma. So the next question, which I usually get asked, so is that working? So is that finished? So is autonomous driving solved? So the answer, of course, is not. So we haven't been solving everything. We have been solving that specific test. So in that specific area, the system works. We have been locating other difficult scenarios and structures that really need more research. So we haven't been solving the whole thing. So we have been solving one specific test. And I would like now to conclude with a video clip. It's a video clip that summarizes the whole test and gives you an idea about the difficulties that we had to face during this test. happened on July this year, and we are trying to do most of that thing today as well. So we didn't have much time to prepare because we came here in Denmark a couple of days ago. We tested that, and today we're kind of trying to do some urban driving with some of those difficulties that we met a couple of months ago. So this is our next vehicle that we're trying to equip with vision again to do 3D reconstruction again. Unfortunately, currently we don't have maps, and this is something that we would like to add. So integration of maps, of detailed maps, is the next step. So we're mainly being reactive to the world, but we would like to include maps to locate ourselves in the world in a much better way. And I will finally show you the system that we have. It's a very simple system. It's 2 cameras with a board, which is a kind of PC. And this is the system that we have on the vehicle right now, but the next version is based on a single board that does everything. So this is what I mean with low cost. It's just a custom board with the 2 cameras, stereo cameras, and the processing is done on board, and that's it. So you don't need any other special piece of equipment to do the processing. So today we're going to give you a demonstration of the vehicle. The test, well, this is not the technology we're using today. It's a different technology. It's a technology that I was talking about before. So the test that we're going to give you today, we'll leave from the castle and end up here. And that will happen around 1 o'clock. So we will leave at 1:20 by the castle, and then we will be moving on that path. It will take maybe 5 minutes, maybe 10 minutes, depending on traffic, and we will be arriving here around 1:30, I guess. So you're all welcome to join us at the arrival to experience the vehicle, see the vehicle, and see what's happening on the vehicle today. Thank you very much.
Thank you very much, Alberto. We have time for a few questions. Just before that, in Danish. Jeg vil bare lige gøre opmærksom på, at den førerløse bil, som kører en demonstration her i Kolding, vil ankomme heroppe bag ved teatersalen i rundkørslen på omkring det tidspunkt, Alberto har sagt. Altså hvis I er deroppe omkring 13:30, så skal I nok kunne se, at hvis den kommer, så kommer den 13:30. But any questions for Alberto? We have a few persons with a microphone. Yeah.
Regarding the cameras that look ahead, what about objects coming from the rear, like bikers, and when you have to make a right turn, you have to navigate and look behind you?
Yes, you're right. Currently, we have cameras looking, we have stereo cameras looking forward and backward, and we have monocular cameras looking sideways. But on the new vehicle, we will have stereo systems all over. So we will cover 360 around the vehicle with stereo. And this is a really important thing, because we need 360 coverage all around the vehicle, no matter what. You really need that for oncoming bicycles, but also for roundabouts. Roundabouts is something that is hardly considered. For example, in the US, you may know that there are not many roundabouts there, and most of the laboratories working in the US are just forgetting about roundabouts. But we do have a lot of them, in Italy and also here in Europe. So we are, very cautious about roundabouts, because that's huge, complex behavior. Okay, the question was about speed limits. We do have speed limits inside our very simple map. So now we have a map which is just a kind of topological map that gives you just connections. We have augmented the map with just a few information, like, for example, the speed limit, but not more than that. But this is the farthest step we would like to take. So take very detailed map and use them. But not only maps with information about the width of the lane, but we will also have information about the behavior that you have to take on that specific stretch of road. For example, 2 ways, 1 way, number of lanes. So we would like to augment the map in that way, because that's the way in which the vehicle will be using with the best use of the map. Yeah. We have the speed limits inside the map now.
It seems like a very interesting project you have there, but I guess you haven't sold any car yet.
I'm sorry?
You haven't sold any car yet. So
no, unfortunately not.
And you have been working on this for 15 years, using a lot of cars, a lot of expensive technology.
Yeah.
Who's financing this? How are you doing this?
We are well, I had a very nice EU grant, a kind of prestigious grant, ERC grant. But the most important thing is that we are working with car makers, vehicle makers. So they are really interested in this. Again, the technology is not mature enough to be sold on the market, but there's a huge interest. And, maybe you have heard in August this year, there was Nissan make a very strong claim that they will be selling autonomous cars by 2020. And then after that, many others followed, like Mercedes did this kind of statement. So car makers are now, committing themselves. And and it's very nice, because I think that's a really breakthrough, because that means that the car market is seeing this as a profitable way. It's a kind of nice business model. So before that, there was just crazy professors doing the crazy roboticists that were doing autonomous cars. But after that, the car market really, committed and said, well, this could be interesting things to do. And if the car makers really want to do that, it will happen. So I'm seeing what happened last August as a really important breakthrough. And there was another one in 2010 when Google got involved in this. So before Google, again, crazy professors doing crazy things. But then Google came into the play, and that showed that, this could be a really interesting thing to save lives and to do more things, to have a more advanced level of mobility for the future. So that was the first one, and the second one was last August. So now everybody's committed, fully committed to that. And I'm not sure if it will be Nissan or Mercedes that will be reaching that level by 2020 or even before. But I'm sure that one day all vehicles will be autonomous. Maybe 30 years from now, 40 years from now, I don't know when. But that will happen, because there's no reason for that not to happen, because technology is improving. We are getting more and more electronics in the vehicle right now. So the next step will be, okay, just remove the driver and have the vehicle drive by itself. So that's something that's going to happen. So we haven't been selling any cars now, but I hope someone else will be doing it in the next future.
Ja, det var vist det for nu. Jeg håber, vi ses op på parkeringspladsen 13:30, og så satser vi på, at der kommer en bil forbi uden fører. Lad os se, vi satser. Tak for nu.
Thank you. Thank you. Good. Thank you.